Okay, so this right here, this is that unknown one where we would have assembled the pieces together. So last time we were doing this one right here. And so we would have looked up these positions right there, right? And we got different pieces to this puzzle. Specifically, these were our pieces, right? So we got that we have some sort of CH3 because its position was 1.1-ish. And then this had a relative integration of 1.5. That would mean that if we took our total intensities, our total integration for this entire thing, we divided our number of hydrogens here by that number, we would have found out that our total integration was 2 times the number of hydrogens, right? So for every 1 integration here, you have 2 hydrogens because our total integration adds up to 6. So we would go ahead and figure out the number of hydrogens that these would be accounting for. So for example, these ones right here would be 3 hydrogens. That means we just have 1 methyl group, right? This one right here is a CH2, which is a methylene. That means we have 1 methylene, don't we? Okay. And right over here, we have an HCO. We have 2 of those protons. Most likely, that's going to be a CH2 right off of an oxygen. Is that making sense? Okay. Now, theoretically, we could also have like a CH, right? But that would be much more interesting, much more rare. Okay. This would be the most common sense one, especially since we have a triplet here. So that indicates we have a CH2 next to it. So the next one we have here is a very high 7.4 to 8.1. That corresponds to your double bonds, right? Aromatic or double bonds. Considering the high IHD here, probably aromatic, right? And so we go ahead and look at the number of protons, and we'd find out, hey, that's 2.5 for the integration, and that would give us 5 protons. That's very consistent with an aromatic ring with something off of it, right? 1 group off of it. The other part of this, the splitting pattern, is going to be pretty complex in this because we're going to have like doublets within doublets sort of thing. Because we're going to have different environments for all of these, right? And so they're going to affect each other. So we'll have a pretty complex spinning pattern that's not just a nice Gaussian pattern. Okay? And so that helps us sort of pin that down. All right, so now we have these fragments right here, but how do they assemble? Okay, so we have a CH3, right? It's always good to start at the things that are at the endings. Okay? So what are the things that have to be at your endings that don't connect to other stuff? Well, they have to be CH3 on one side, doesn't it? And the other side would have to be this group right here, wouldn't it? Benzene. Okay? And so what do we have left? Well, we have a O in CH2, and then we have another CH2, don't we? Okay? So it has to be something like a O, CH2, CH3. So it has to be something like an O, CH2, CH2, CH3, right? We couldn't have it reversed, can we? Can everybody tell why we can't have it reversed? Could we have the O in the middle? So let's say we had a functional group that looks like this. Does that fulfill the things we have right now? This one. That doesn't work, does it? No. Because that would mean these would be the same. Or at least very similar. Okay? And so this right here fulfills what we have over here, doesn't it? We have 2 hydrogens here, right? 2 of them here, and 3. We have an O going off to a CH2, and then a CH2 going off to another CH2 donor, and then a CH3 after that. So that right there would fulfill these requirements, wouldn't it? Okay. All right. So we can go and put together our propoxy group. Propyl off an oxygen, right? Okay. And notice again, if we were to look at this group, right, we would see that it's actually just an extension of these. Now, let me ask you in terms of splitting patterns, does this make sense? So when we looked before, right, that CH2 here was a sextet, wasn't it? Okay. And so how many hydrogens did that CH2 that's not next to the oxygen need to have? 6 minus 1, right? And so that would be 2, 5 right here, right? And that's building proof for this structure, isn't it? So this structure is consistent with that. If we were to look at the one next to the oxygen, that's a triplet, isn't it? Okay. And so the ones next to it is 2 hydrogens plus 1 would give us a triplet, wouldn't it? Okay. You see how I'm going through? I assembled a structure, and then I'm proving if that structure makes sense. Okay. Okay, and so the next part here, these ones right here would be your benzene ring right here. And you'll notice that, again, this is a complex structure. This right here being attached as the next side of this. Would give you a complex structure, wouldn't it? These ones would be shifted quite a bit. These ones a lot less. These ones the least, right? And then you'd have splitting from this and this. You'd have splitting over here as well. Mm-hmm.
What's the peak that's a little bit past peak? Is that also part of the benzene?
Yeah.
Okay, so that whole thing is.
Yeah, these are our benzenes, yeah. Yeah, you actually have 2 fairly chemically distinct ones here. This one's going to have an oxygen here. Then these ones are going to be fading off of that. So yeah. Yeah, you actually have more of a separation. Yeah. So these are influenced by the oxygens right there. Yeah, stretching, scratching, and questions all look the same, don't they? That's life. Okay, so this right here is your puzzle pieces when we finally assemble it. So again, we have our CH3. Off of that is a CH2. Off of that, we have another CH2. And we finally have an oxygen that needs to go on that. That's the propoxy portion, right? Once we get that, then we realize we only have one other part of this that we can deal with, right? And that's that we have to join it to the benzene ring somehow, right? I skipped the part that doesn't have a hydrogen right here. Okay? Because I was just assembling my pieces so far. Okay, so if you go back through, man, these things move around. So good. All right, if we go back through again, so we have our pieces together so far. We have our benzene ring. Okay. We have right here the propoxy group, propoxide group. Excuse me. All right. So how many of our atoms has this accounted for so far? Yeah. So 1, 2, 3, right? Count for 3 carbons here. It's another 6 carbons here. That's our 9 carbons, but we need 10 carbons, don't we? So we have another group that doesn't show up in our HNMR, so it can't have any hydrogens, right? and that has a carbon on it. Okay. Okay. And so how many oxygens have we accounted for? Here? No oxygens. So we need to account for one more oxygen, don't we? Okay. For it to not have a hydrogen on it, what does that oxygen need to look like? Yeah, we have to have something that bonds around, right? Okay. And so our options would be something like this or like that, right? Ketone or aldehyde or carbonate, right? Ketone and carbon. Okay, so we go ahead and look. Is there a problem with this one though? Yeah, if we had, we would end up having hydrogen, right? So we can't have that, can we? Yeah, we didn't have any hydrogen there. Okay, so that one doesn't make sense. We're left with a carbonyl so far, right? Okay, so we have how many hydrogens taken care of so far? 3, 2, 5, right? 7. Okay. And how many hydrogens here are taken care of? 2, 3, 4, 5, right? Okay. This is verifying that we don't have any hydrogen peaks, by the way. And so 5 plus 7, that's the 12, isn't it? Yeah. So we verified that, yeah, we shouldn't have seen any more hydrogen peaks. We didn't have any more hydrogens to take care of it. So this does not have any hydrogens on it. If we go ahead and assemble our groups now, the only places where we can bond these two bonds here that are remaining for that carbon are these ones here, right? And so we assemble all our pieces. Like so. Is there any other way we could assemble those? No. Yeah, we could flip the whole structure, but yeah, it doesn't do anything. Okay, and so we got our unknown, don't we? Now you will note that having like a C13 as well, or an infrared as well, would have made this process shorter, right? And would have made this process a little bit easier. Okay? Because then we would have had information about that carbon, right? And not just had to deduce it from everything. But you can still do this with this problem with this, just the HNMR. Okay, so again, these are the steps. And so let's try this again. Unknown 2, we're going to have a C13 in this case. We also have an infrared with it. And the overall formula is C5H12O. I'm going to go ahead and let you start this. So start getting an assignment, start getting your fragments together. You'll need the book, obviously, table for the NMR peaks. This is DEPT, by the way, DEPT. And to help you out, they've done the work where it would have done the intensity integrations. They've just told you the CHs rather than making you try to figure it out. So normally you would have taken these intensities, right? And they would have told you how many hydrogens were on those. But they've done this for you here. Notice that last peak is not assigned here. DEPT especially typically has a solvent as well. So almost always you're going to end up with some small solvent peak out here. And that's what you're seeing there. And what's the 0, by the way? That's TMS, right? Also don't need to account for that one. By the way, in case you're curious, the solvent here is CdCl3, which is that small peak right there. This will actually wrap up the chapter, which is why I'm making you actually like do this here and really double check, make sure you have the tools. And then please ask questions if you have any questions. Remember, I have office hours Wednesdays and Thursdays really well, almost most of the day. We'll end up starting up on chapter 8 after this. Well, chapter 8. Generate those fragments. You very much can talk, by the way, and help each other and like teach each other. That's some of the best studying you can do. I don't know if that was good or bad, but look. Did anybody do the IHD yet, by the way? What's our IHD for this one? 2 times 5, 10 plus 2. So we're fully saturated with hydrogen. Which tells us we don't have rings, double bonds, triple bonds, right? I'm going to go ahead and sort of start working forwards, but I want you to still be thinking ahead, okay? Try to assemble it before I get there. Beat me, all right? You'll get more from this. So how many unique peaks do we have in this case? 3. Yeah, it makes it real easy to label that, doesn't it? Yeah. So we have 3 unique peaks in this case. Do we know the numbers of them? The number of carbons that are involved? Like, is this 3 of CH3s, 2? We don't know. Not from this information right here. Remember the intensities for DEPT, because of that decoupling, don't actually have any meaningful number of carbons. Okay? It actually has to do with the number of hydrogens that are around it, right? And they've given you that right here. They've done the work of extrapolating that. Mm-hmm. No, it does. Yeah. Yeah. Otherwise, the only carbon it could show is this one. Okay. So let's go ahead and go on to the next one. So we don't have any nearby double bonds, right? We can't have any double bonds for the carbons. Okay. And if we look up the chemical shifts here, we see that this chemical shift here, which is the 26, that's this stuff right here, right? That corresponds to a CH3 bonded to another carbon, which you guys probably realize that. So we have some CH3s, right? Not sure exactly how many, but we have some CH3s. The other thing we have here is we have a 33-ish peak, that's this one here, that has no hydrogens on it, right? And so what that would have to be is a carbon. In this case, it has to be a carbon with all carbons attached to it, because it's not shifted very far. It's really close to the 26, isn't it? So only other carbons attached to it, non-oxygen. Okay. Okay, so then we have a peak up at 73 here. That's this high one right over here. And that tells us we have something pretty electronegative attached to it. Or it would be like a very low peak for something like a double bond. But double bonds would be very much higher usually. So this right here would mean that we have some sort of carbon-oxygen attached to this. In this case, it's not going to be involved in a double bond. Like I had mentioned, if it was actually in a double bond, it would be even higher. Okay? And so this tells us we have like a OH attached to that carbon. And it's a CH2, which was given right here. Okay. Okay, so these are our current molecular fragments. Is everybody okay with that so far? Fantastic. Fantastic. Okay. Not losing anybody? All right, so the obviously that carbon that's surrounded by other carbons, that has to be attached to those other carbons, right? In some way. The CH3 is attached to those other carbons. The CH2 can't be attached to a CH3, can it? No, because then the chain would end. Okay? So, we don't have just a normal CH2, do we? Everybody see that? We don't have a CH2 that would be between two carbons, do we? That wasn't something we ever got. Okay? So we actually got some extra information because we have an absence of a CH2 peak that's just attached to carbons, don't we? Okay? And that's that this has to be attached to the carbon that's attached to all the other carbons, doesn't it? Okay. So those are our fragments so far. We're going to go ahead and start assembling our fragments. And so we go down here. And we have to have CH3s that are attached to this carbon, right? Anytime a CH3 would be attached to another CH3, we'd end our chain, wouldn't we? Okay? CH3s are always endings of chains. And then our oxygen attached CH2 also has to attach to that central carbon. Is everybody okay with that so far? Okay. And so what we end up doing is we have the OH CH2 that attaches to our central carbon. The CH3s go around it, and that gives our final structure. Okay. Does that make sense how I assembled those? Um, 9, 11, 12. Yeah. The OH, yeah. So be careful about the OHs, folks. This is why oxygens don't change the saturation, by the way, is because if they only have a single bond, the H just goes on the other side. So they're like little H extenders, right? Okay. Anybody have any questions? Mm-hmm.
the the original CNFR?
Mhm.
How did they get the peak near 73 CH2?
That's actually from the DEPT. So that would have been the integral as you go up. You would have been able to get that information. Yeah. Typically, what happens is to make life easier for people, um, you just go ahead and assign the CH2C, CH3s automatically on the spectra. And in fact, some instruments will do that for you.
I
Yeah.
imagine that it would be, right?
No,
Oh,
most
okay.
likely. Yeah. Yeah. Only if I'm specifically making you do an integral measurement. Most exams will have it like that. Most exam questions. Just because then I can put the spectra in smaller, right? Otherwise, I have to give you a spectra that's like. Yeah. So this is actually the more common way to see these. Or you'll see this as a very thin band with just the lines, no intensity. And then you'll see the C's marked under them. Okay. And so typically you do see it like this. Actually, it's very common. Okay. Any questions, concerns, comments, party tricks? Oh, okay. Let's go ahead and go to the next chapter.